on Professor Joshua Bengio of the University of Montreal, who has done a lot of work on neural networks and especially now has great results for statistical language modeling. He got his PhD under Renato De Mori in '91 from Bengio University. Since then, he was a postdoc at MIT with Michael Jordan and also at AT&T, and he's been a professor at the University of Montreal since 1993.
Thank you. So I will tell you about some of my work in my expertise is really in statistical machine learning, and in the last couple of years I've been toying with language modeling. Although in my baby research days I did some speech recognition, I didn't really know as much as I do now about language modeling, and probably many of you guys will be able to give me interesting comments and critiques, and don't hesitate to interrupt me, especially concerning the language part. Okay. So I will try to explain to you what I think is the interesting and the greatest challenge in this statistical language modeling business, which has to do with the curse of dimensionality, what people call the curse of dimensionality in machine learning, which has to do with representing the joint distribution of very high dimensional data, which requires to say something about objects that you've never seen before. And I'll try to convince you that the kind of methods that most people have been using in statistical language modeling based on essentially probability tables are not going to scale up if you want to consider a lot of interactions between many variables. And one way to face that is to look at distributed representation. So I will try to explain what I mean by that and how that could be used to deal with very high dimensional dependencies, statistical dependencies. I will try to summarize my view of what the job we have to do is in terms of taking probability mass from the observed data, which is the empirical distribution, and trying to spread it smartly around in some kind of neighborhood in different ways. And trying to see how it has been done with different language modeling devices. I will tell you about a particular set of experiments I've done with neural networks to try to deal with this curse of dimensionality in the simple case of an n-gram-like problem. Then I will spend some time trying to understand a little bit why it's working and how it's related to other things like maximum entropy models. And then I will try to address one of the main problems with these neural networks applied to such language models, which is speed. They currently take huge amount of computation in order to train and even to compute probabilities. And so I'm investigating different sampling approximations to try to make this 100-fold or 1,000-fold faster than it is currently. Then I will talk about some recent work where I'm trying to go beyond the n-gram kind of model and trying to put in information about ambiguity, about polysemy, and about ontology, the kind of thing you get in WordNet, for example, into these kinds of models. And one of the first steps is just forget about the neural network and just see how far we can go by using the information we have in resources like WordNet to do smoothing of probability of bigrams or n-grams. And then we'll see how that can be generalized to neural networks and some ideas to use this kind of thing within stochastic grammars. All right, so I probably won't have time to cover all these things, but please interrupt me whenever you want. Okay, so what we're trying to do in statistical machine learning is design some learning algorithms which take data and possibly prior knowledge and output some function. Then we can use this function in some domain, and we can measure some loss which depend on some random variable, and then we would want to minimize that loss. In the case of learning probability function or density estimation, the typical loss is the negative log of the probability function or the density function, although some people have proposed other losses. For example, L1 loss has been proposed for density estimation by Devroy. And if you want to do other problems like regression or classification, you get other losses, but many algorithms can generalize across different types of losses. But today I'll be talking mostly about estimating probability functions. All right, now the really interesting part about statistical machine learning is this notion of generalization, which is you're given examples which tell you, for example, in case of probability function, that that some things are probable, the things you observe, but really what you'd like to know is how probable are things that you've never seen. In the case of regression, you have some input cases for which you know what the right answer is, or some noisy value of what you would like to get, and those, for example, those pairs or those points are your training examples. And generalization in this case means, well, someone gives you a new input x, and you're trying to predict what's the correct output for this y. And in this simple example where the input is one-dimensional, it's very easy. Any learning method will tell you that the correct y is somewhere around here, because you have other examples in that neighborhood which have these values of y. So basically any kind of interpolation will work. So with low dimensional data, all learning methods essentially give the same kind of answer, and they all work well. And you can use very simple and easy to analyze mathematically methods like non-parametric regression or non-parametric density estimation and get quite decent results. The thing gets harder when, first of all, you go from continuous to discrete, and second, when you go to high dimension. Well, discrete, it's hard because sometimes you're going to get symbols that you've never seen. So suppose you wanted to associate letters with a binary digit, and you've seen these in your training set, and someone asks you for a new symbol you've never seen. And of course, in language modeling, we have to deal with that. But the really interesting case, so you see why it's going to be more difficult, because you have like no inkling about this thing you've never seen before. Now, in high dimension, typically everything is going to be new. Every new test case is going to be a combination of values that you've never seen, whether you're in discrete or in continuous case. But the interesting thing is that why it becomes difficult, even in the continuous case, is that generalization becomes a problem of extrapolation rather than a problem of interpolation. In other words, the new data points are not going to be sitting nicely in the middle of other data points that you've seen before. That would be interpolation. In other words, I'm going to ask you something about, say, a new sentence in English, and it's not going to be in some space. It's not going to be simply sitting within the convex hull of other sentences that you've seen. It's going to be more like on the border of the things you've seen. It's going to be on the side. Everything is going to be on the side. In high dimension, everything is on the borders. And so you have to extrapolate from the stuff you've seen to things that is quite different and not just linear combinations of the things you've seen before. All right. Graphical models are ways to represent joint distributions. And you've probably seen this kind of representation. If I want to write the joint of Z1 to Zn, I can decompose it as a bunch of conditionals of Zi given some subsets of the previous ones, which we call the parents. And if you choose a small enough subset of parents, so this is a graphical representation of the same thing. I have Z4 here, which I'm going to make depend only on 1, 2, 3, and not on the others. If the set of parents is small enough, then you can use tables to represent these conditional probabilities, and everything is fine. Unfortunately, if you have many random variables and you don't have a lot of prior knowledge about which are the conditional independency, in other words, which variable you can throw out in trying to predict Z4, then these tables becomes very large, and it becomes difficult to handle. You get overfitting, and you need to smooth, and you're facing the curse of dimensionality. So there is a thread of research which has not really been pursued enough, I think, to try to deal with this, learning these high-dimensional probability functions, in which the idea, and this is the idea that I'm going to come back to with the neural network later, is we have this probability function, which is a function of many discrete random variables in the case of language. And instead of looking at all the possible combinations of these random variables, which is hopeless, what we are going to do is we're going to approximate this function using a sort of a constrained set of class of function which cannot represent all the possible probability functions. And thus the number of free parameters will be not exponential in the number of variables. It will be something we can manage. And we will get automatically, because of this approximation, generalization to the cases that we've never seen. And this is what you find, for example, so there are at least two methods that are established now. One is based on, well, both are essentially polynomial approximations. So the idea is you can take your probability function, and if you write it as a polynomial expansion, so P of Z1 to Zn is actually a polynomial of order n. So if you have n variables, really the probability function, the whole table, you can write as a polynomial of order n. And you get the full, there's no approximation. So you could approximate it by a polynomial of order d. Okay? So that's the idea of these methods. And of course, typically d is 2. Because, or if you have lots of data, like in language modeling, d is going to be 3 trigrams. All right. Now, the thing about these, so essentially, what a polynomial of order d is doing is representing explicitly all the combinations of values of d tuple. So we take d at a time variables, like the last two words, or the next word and the previous word in the case of a bigram, and we look at all the possible combinations of values, and for each of these combinations of values, essentially we have a coefficient in our polynomial. And so the number of degrees of freedom is exponential in the size of the tuples, and furthermore, if you care to choose which tuple you want to look at, which in the case of n-grams we don't, because we say, well, we just look at the previous context, but in other cases you don't know which subsets of variables are important, like in lexicalized stochastic grammars or other cases, then you have to search somehow, and this is also what you do in maximum entropy models. You have to search for good tuples, and this is also an exponential space in this number of tuples. So it's difficult to work with that. Now, once you've settled for a particular choice of tuples, estimation of parameters is quite easy. You can use EM or you can use whatever method. Typically, it's easy to estimate parameters. It's just counting. Now, this picture here is telling us basically that this kind of representation with tables or polynomials is local. So what happens is, if I just look at a bigram, one way to think about the bigram is I have a very long, stupid vector with all zeros and 1 at a position which corresponds to the particular word that I'm looking at. And then there's another word, say the next word, which occurs in a different place. And then I have a table of probabilities, and there's going to be one entry which is going to be activated. So there's one entry in the table which becomes active when a particular event happens, and that's all. And there's going to be one free parameter for that entry. So I'm going to call this a local representation. And the reason it's local is that what I'm learning for this particular entry here doesn't tell me anything about other entries, except if I'm doing smoothing, which is going to tell me something about everything in that row and everything in that column somehow. So smoothing helps to deal with that. But there are other ways. So one way is to think about these distributed representation, which for now is just a magic word that I've been using, and I'm going to try to explain a bit better. But one thing about these representations, unfortunately, is that we're going to lose some nice computational features that we had with the tables. They're essentially going to be more difficult to optimize. So that includes things like neural nets, like distributed generative models. These are graphical models in which you have hidden variables, and these are max entropy models, which are kind of in between tables and these neural nets kind of thing. All right. So let me say a few words about neural nets. So they are one way to represent, with a few degrees of freedom, high order dependencies. So we have this huge table. If we take many discrete variables, we want to learn this function, and one way to represent that function is with a neural net. And typically, what are neural nets? So here's a usual instance of neural net. So it's a class of functions, and we can do many variants, but this is like the most common class. So x is a vector, could be discrete or continuous, and f could be also a vector. And we're going to take this vector and apply an affine transform. This is the first layer here. So here's our input vector. We're going to apply an affine transform. Then we're going to apply nonlinearity. So the hyperbolic tangent is simply something like that, sigmoid. We apply nonlinearity, and then we get another vector. The nonlinearity is applied element by element, and then we do another affine transformation. So this is a matrix, this is a vector, this is a matrix, this is a vector. We apply this other affine transformation, we get another vector, and then potentially we do another nonlinear transformation if we need to. But this one is not necessary. It depends what we want to compute. So for example, if we want to compute probabilities and we want these things to be numbers that sum to 1 and they're positive, then we choose a particular nonlinearity here called the softmax, which gives us these properties. All right. And so we have a class of functions with some parameters, b, w, c, v, whatever, all these numbers that come in the formula. And then how do we find these parameters? We define a loss function which tells us for a particular example, we would like, say, the output of the function to be high in some cases and low in some cases or whatever. So we have a loss function which tells us for a particular input the kind of thing we would like to have somehow. And we sum the loss over all the examples and we try to minimize that. And in some cases, to constrain the class of function even more, we can add some penalty. For example, penalize the sum of the parameters, the sum of the squares of the parameters. This is called weight decay. Now, the interesting thing about this class of function, there are many interesting things. Well, first of all, it's a universal approximator. So in theory, if you were able to do this optimization properly, you could approximate any continuous function as long as you had enough of these hidden units. As long as this first projection was to a space with enough dimension. So the number of dimension here can be larger than this. Okay, it doesn't have any, it's not bounded. You decide usually ahead of time how many you want to put, but having chosen that, you've essentially chosen the precision with which you're going to approximate your function. So if I want to approximate a probability function, really what I'm doing is by choosing the number of hidden units, I'm choosing the precision with which I'm going to approximate the function. I'm choosing what's called the capacity, the number of degrees of freedom of the class of functions. Okay. Now, an interesting thing to note here is that if I increase the number of variables, then the number of free parameters doesn't grow exponentially like we had in the table. It's going to grow just linearly.
If you leave h the same, right?
If h is the same. But of course, you actually have the freedom to choose h. So you can make, if you make this bigger and you want the same number of degrees of freedom, you can make h smaller, right? So you have independent control. The number of degrees of freedom is not dependent on the number of inputs. And that's good, because really the number of degrees of freedom should depend only on one thing, which is the amount of data you have. This is really, learning theory tells us the more data you have, the more degrees of freedom, the more free parameters you should be able to afford. So we have decoupled the capacity from the, if you want, the dimensionality of the input vector. Even if we have very small amount of data, in principle, we can capture some high-order dependencies. Now, let's try to compare how this is working with, let's see, what we had with the tables and the polynomial approximation. In the case of the tables and the polynomial approximation, what I was doing was I'm going to restrict myself when I'm doing an approximation with a polynomial of order d, which means I'm going to take d variables at a time. I'm restricting myself to all the possible dependencies between those d variables. In other words, all the combinations of values, I'm going to have a free parameter. And so for all of these combinations, I'm going to be able to capture all the possible statistical dependencies that there could be between these d variables. But then I can't say anything about the higher order dependencies, which mean the dependencies which involve more than these d variables. Whereas with the neural network, each hidden unit is essentially capturing one or something like one high order dependency. Could be a low order dependency. Each hidden unit has a fixed capacity. It has just one vector, as many free parameters as there are inputs. So each hidden unit is capturing one aspect of the data, which could be something about its distribution that relates all of the variables together, or maybe just a subset. But that's going to be decided by the learning. So the number of dependencies is limited by the number of hidden units you want to put in. But these dependencies could be of low order or of high order. And that's going to be chosen by learning, by optimization through the data. Is that clear? Yes.
A couple of questions. So
yeah.
On the one hand, the number of inputs, it depends highly on how you encode the input into the neural network. Since
yes.
It's a highly parameterized form, and
yeah.
there might be some
there might be some better ways than others.
Which
yeah.
are much less efficient than
yeah.
others.
Yeah.
And secondly, the dependencies are still in the hidden layer highly constrained by the number of hidden units.
Yeah. Well,
so,
each hidden unit is.
I mean, unless you've got a way of learning the number of hidden units, it's not.
Oh, well, there is a way, which is the trivial way that most people use, which is you gradually increase the number of hidden units, and until you get the best results you can. At some point, if you have too many hidden units compared to the amount of data, then you're starting to overfit, which means out of sample data, you're doing worse than if you had less hidden units. So there is a standard way to find that out, which is kind of expensive, but not that much. If you don't have to try like 20 hidden units, 21 hidden units, you double, and quickly enough you find a good range of values. Okay. So, well, one way to see that you get possibly all the high order dependencies is that if you take a Taylor expansion of this hyperbolic tangent of the dot product of the input with some parameters, you get a Taylor expansion which depends on all the products of the input elements with themselves. But with the constraints is that you only have actually a few degrees of freedom to choose. Now, so each hidden unit is quite limited in what it can represent, but it can represent any particular one high order dependency that you care about. But one thing it's doing also is that it's going to respond with a high value not only when a single combination of values is presented, but a whole subset of the input space because this is essentially a projection. So any combination of values here that is in some sense orthogonal to that projection in some way is going to yield high value here. So there's a large subspace for which you get high values. There's a whole half space actually for which you get high values. Now that half space may contain only a small subset of the possible values here, or it may contain a large subset of the values. And now the universal approximation theorem tells us that if you take enough of these guys, you can approximate any function. Of course, it may not be practical. It may be that the difficulty of estimating those parameters is such that you don't actually solve your problem as well as you could. So we are trading off expressiveness, which is very powerful, because with a few degrees of freedom we can capture a lot of high order dependencies that are most relevant to our data. But what we're losing is now we have a difficult optimization problem. Now, maximum entropy approaches are kind of in between. In a maximum entropy, one way to understand this is that the hidden units are like the features in the maximum entropy model. Okay, so in the maximum entropy model, what we let's say what we have is something like that. So we represent the conditional distribution by taking linear combination of fixed features of the variables of interest and then normalizing over whatever we want to get the proper conditional. And we learn separately those linear combinations parameters and the features. Now if you look at this, basically the features are like those hidden units in some sense, and the lambdas here, the weights in the maximum entropy model, are just like those weights at the last layer. In the neural network, we're learning simultaneously those parameters and those parameters. In the maximum entropy model, we're saying, well, suppose these guys are fixed, and then learn those guys with a good method, because this turns out to be convex optimization, so we can quickly converge. But then we have to select those guys, which is a difficult search problem, and we have this embedded difficult problem where we have to, in the inner loop, we have to choose these guys, in the outer loop, we have to choose these guys. So there are a lot of similarities, but the way to optimize is quite different. And in the neural net, we're essentially optimizing both at the same time. Another difference is that in the maxent model, because of the way we're doing the search, typically these guys depend only on a subset of the variables that are here. It's easier to search that way. Whereas when you look at the parameters here, typically actually each of the hidden unit is going to depend on everything. Maybe putting some more weight on some of them and less weight in others, but typically they depend on everything. Yeah.
So a support vector machine is also not a case where the hidden nodes are determined from, in this case, from a training set where they select.
So in the support vector machine, the hidden nodes, in the support vector machine, what you're doing is you're constraining those vectors to be essentially examples. And you're using an optimization method to tell you which subset of examples, which are the support vectors, correspond to those hidden units. Okay. And which turns out nicely to be, again, a convex optimization problem, so you can solve it in a reasonable amount of time. The problem with SVMs in the context of natural language statistical modeling is that typically the number of support vectors you need in support vector machine is quite large. It's a significant fraction of the amount of data. It doesn't compress the data as much as things like neural network do.
It depends how noisy the data is. Right?
Yes, it depends how noisy the data is. And in language modeling, it's quite noisy because we can't really predict well what the next word is going to be. So I didn't try it on language modeling, but I do a lot of work with SVMs, and it's just for me hopeless to train an SVM with more than 1 million examples. In fact, one of the research topics in my lab is trying to train SVMs on large data sets, order of 1 million or more examples. But typically, if you have a large corpus in language modeling, it may be tens or hundreds of millions of words, and so SVMs are going to be hopeless. They essentially are going to store a good subset of the data directly. But there may be ways around. Another problem is not just storing, is the convex optimization problem for SVM. Takes at least n squared computation where n is the number of training examples. Okay, well, there are ways around that, but not really yet working perfectly, and that's actually one of the things we're doing in my lab as well. But typically it's very expensive. If n is large, if the number of examples is large, then SVM's training time becomes horrendous.
But it also depends on how you choose the kernel function in an SVM, because...
Well, for any kernel function, if you use the straight SVM, just representing the matrix is n squared.
Yes,
and
if you select a kernel function which includes like part of speech tagging, like if you use like nouns, phrases, and then make a kernel function out of it, then it's possible that the dimension of the actual kernel function is so less that SVMs, they converge pretty fast. So
it might converge pretty fast, but even one iteration of the SVM learning costs you n squared.
well, it's the order of support, it's number of support. Depending on how
Okay, well,
The inner product matrix might have a sparse representation.
yes, okay. So there may be ways around, but and I'm not saying it's not going to work, but let's say I was a bit discouraged by trying a few things, and yeah.
Yeah, I was confused by something you said earlier. You said that I guess the number of degrees of freedom in the neural network is the number of hidden units.
Well, it grows with the number of hidden units. It grows linearly with the number of hidden units.
And the input time is the input.
Yes.
Okay.
Yes.
So you don't really get the extra amount of representation for free, like.
Well, it grows, so the number of degrees of freedom, if you keep the number of hidden units fixed, grows linearly with the number of inputs, which is quite reasonable. I'm ready to pay a linear price for. But you can always, as I said, you can keep it fixed as you increase this, you decrease that, in principle. All right, let's move on because I have actually a lot of things to talk about. Let's skip that. Well, I'm just going to summarize the previous 2 slides with one slide, which is how to generalize in probability space. Essentially is taking probability mass from the empirical distribution and spreading it around in a smart way. And so around means some kind of neighborhood, and we have to define smart neighborhoods to get good generalization. So one way is to say, well, just look at a simpler model, for example, in the case of table that only looks at less variables. So we're going to just, we have our table and we're going to say, well, we're going to automatically give some mass that goes in one place to everybody in the same row and everybody in the same column, okay? Which is kind of, kind of strong. You're going to lose a lot of probability mass by doing that because it's kind of blind. But in some sense, we always have to do a little bit of that because otherwise we risk giving 0 probability to some things that we've never seen, and we don't want that. Another idea is what is exploited in the n-grams. I mean, the reason n-grams are generalizing essentially is that from one training sentence, I can generate other. Well, the way I can generate a new test sentence that I've never seen essentially is taking pieces that I've seen in the training set, like the cat walks in and so on, and just putting them together in such a way that the pieces overlap and are consistent with each other, and these pieces will be chosen with more probability if they were more frequent in a training set. So the only kind of generalization we get is by saying, well, we can generate a new sentence by pasting small pieces that we've seen before in a consistent way. This is essentially what n-grams are doing. Another way to get generalization is to take advantage of the fact that there's some words have some similarity with other words. So if I've seen the sentence, the cat walks in the bedroom, and I know that the and are kind of replaceable, and cat and dog are kind of replaceable, and so on, I should be able to generalize from that sentence to all the other sentences which are just similar to this one by replacing one or more words by other words which are similar. So this gives me actually a combinatorial number of generalizations, and we ought to take advantage of that kind of generalization, which is very different from what you get in n-grams. You don't get that in n-grams. You get that in models, for example, that take advantage of clustering of words. But typically, then what you have is a kind of hard cluster in which either two words completely share probability or they don't, which is not nice. So it would be nice to have a kind of smooth notion of similarity to distribute probability mass from words that you've seen in some context to other words that you've not seen in that context, but you've seen in other contexts, and that these contexts somehow match each other. So that was substituting words with replaceable ones. So this is one idea that has been exploited. And another one is substituting phrases by other phrases which have a similar grammatical role. That's what you get with stochastic grammars. If you have stochastic grammars that are lexicalized, you also want those pieces to be consistent in terms of the trigram statistics. And then there's maybe something else which we've not really exploited, which is generalizing from sentences which have a certain meaning to other sentences which have a similar meaning. All right, which of course has to do with capturing very high order dependencies between sequences of words, beyond what you get with grammar and beyond what you get with just the short-term dependencies. All right, so the neural network for language modeling that I mentioned earlier essentially has this kind of architecture. It's designed in the spirit of taking advantage of this notion that similar words I should be able to replace a word by a similar word and get a similar probability. So I'm going to have a probability function which depends on a bunch of words. And I'm going to have this bunch of words. And there are going to be some boxes here with parameters. And there's a first stage here where I'm going to take each of my words and map it to a feature vector. For example, an R30. Okay, so I'm going to take this symbol, this integer between 1 and 20,000, and map it to a vector in R30, for example. So 30-dimensional real valued feature. So for that I need a table I call C here, which has one row per word, and I just pick the correct row corresponding to the word that I'm seeing. And now I have a continuous valued representation in input, and I feed to regular neural network.
Why do you say continuous?
Because these features are not constrained to be binary. They could be real valued. Now, of course, they're only going to take a finite number of values for those words, but during learning, they're going to explore all the possible continuous values. So then we have a black box which is going to output this probability function. But the point of this first layer here is that if I replace any one of those words or all those words by other words which have a similar internal representation, which have a similar set of word features, then the vector here is going to be close to the first one I had. So if I have a training sentence, or a piece of a training sentence here, for which I'm going to learn to put a high probability, because the second stage is a smooth transformation, if I instead put in here another set of word features which correspond to a similar sentence in this sense, I'm going to have a close probability. So sequences that correspond to similar words correspond to similar feature vectors here, which has to correspond to similar probabilities out. So that's how I'm spreading probability mass according to the metric that's in some sense learned here by this word feature, these word features. Yeah.
How do you get that feature vector for word?
You learn it. What?
How do you get that feature vector for a word that you've never seen before?
Well, it's a good question. So I have a theoretical answer. I didn't really try it. The theoretical answer is that once you get there's a way to set up that system here, so that no, let me put it this way. Okay. Here's how you can do it. What you can do it is, in a given context, suppose I know all the previous words and I don't know the next one. Okay? So I can run my neural net. I'm going to get a probability for all the words that I know. Let me call the context HT. And so I can compute the expected code for the next word by taking the codes of all the words, okay, so which are those feature vectors for each word, and then averaging them according to the probability computed by the neural net. So I can run the network for all the words that I know. I can get the probabilities for all the words that I know. And those words that come in the same contexts, similar contexts as that unknown word, are going to suggest a code, right? And I'm going to average them. But anyway,
what is the unknown word in that formula?
It's nowhere, all right? It's WT, which is not even in that set.
Yeah.
Okay? But I'm seeing WT, HT, okay? Now I'm going to just use HT. That gives me a bunch of probabilities for all the words that I know.
Yes.
Each of those guys, and suppose two of them have a high probability. These two words have some word features. I'm just going to average these word features with the weights given by the probability, which is just a definition of the expected code for that context. And you can run that in all the contexts where you see this unknown word, and that gives you an initial code for that unknown word. You can bootstrap that.
Hull of codes.
What?
That lives in the convex hull of codes.
Yes, which is actually not working really well.
You're saying you don't want that.
You don't want that. Actually, I don't think it's going to work for words because of the polysemy problem. Okay? So, I think one reason why, one way to improve a lot, I'll try to say a few words about later, is to put in input not words but senses. Because really each word can have multiple senses, and they should really have a different representation, these senses. And if you have multiple, if this is a kind of is trying to capture all of the senses at the same time, and then you're doing some average in that space, it's not going to be very meaningful. So, but of course, it's a theoretical answer to your question. I don't know if this is going to work. And in principle, there are ways to deal with that. Yeah.
If you do have some belief that unknown word should behave the same, why not just model it as an unknown word? Just throw away some low frequency words, put them unknowns, and just model it as
Oh yeah, well that's the way I do it now. But if you really wanted to learn something specific about that particular word, essentially what you want to do is say, well, in which context is this word appearing? And then we're going to predict which word are likely in that context according to our probability model. And that's going to tell us something about the right feature vector for that word.
But you could still do it by modeling as unknown word.
Yeah, it's much simpler the way you're saying, of course. But then if you model as unknown word, then you're merging all the unknown words in one category. Okay, so you're losing a lot of information potentially. Yeah.
I think the easy way to describe what you're saying is to say that it's that the word itself is a hidden variable.
Yes.
Which is to be inferred by
the word features. Yeah, the word features. Yeah.
Sure, by clamping everything else. So you could learn the word features are always hidden. You're always learning the word features.
Yes.
But in this case, the word itself is a hidden variable. You don't know what input you're providing for that, and you still have to be able to learn an appropriate vector features for that word. I mean, if you don't think about this as a feed forward,
Yeah.
network.
Yeah.
But rather is just modeling relationships among the nodes.
Yeah.
Right, then is what you're saying equivalent to that?
Yeah, let's move on. All right. So this I've said in words. This is just the same thing as before, except now that I replaced the box by a neural net, and there are some details that are maybe not important to describe.
What are your features exactly?
What?
What are your features exactly?
Okay, what I call the features are these numbers that I associate to each word. So each word, this is a number between an index between 1 and 20,000, and this is a vector of 30 real numbers. These are my word features. So each word is associated with such a word, so such a vector of features.
And what's the semantics of these features?
I don't know. I wish I knew.
No, he's going to estimate it.
Yeah, they're learned.
He's going to learn everything about the network, including.
Everything is learned.
Oh, right, okay.
I just do maximum likelihood and plus.
So this is, the network itself is a standard sort of three-layer MLP kind of thing?
Yeah, except for the first layer, yeah.
And then the features are sort of little, what's the parameterization of the features that you're learning?
It's just a bunch of free parameters.
Oh, is there a functional form for the C's?
No, it's a table of numbers because this is just a table access. It tells me which row of C to access, right? This is another way to look at this, which maybe makes it easier to understand, is that you can encode the words as very long, stupid vectors with all zeros except in one place, which corresponds to the particular word. Okay. And then the C matrix comes here. I'm just reusing the same C matrix all the time. And you take C times this vector, which has a 1 only in one place. And what this is really doing is selecting one row or whatever column of C. Okay? And later I'll come back to this representation. So I trained this with maximum likelihood, with lots of hacks to get it to run on parallel machines, and did a few experiments because each experiment takes a while.
Question.
Yes.
So you really don't have a hidden layer then, do you?
Yeah, I do. In some sense, there are two hidden layers. There's this, which are the word features, which is kind of a hidden layer because I learn it. But it's a linear transformation. Okay, I don't need to have a tanh here. And then there is a regular neural net hidden layer. Is that okay?
I think the reason there is puzzlement is that people don't know how you're going to choose the C, at least what even the initial thing is.
Random.
No, I know what the answer is because I read the paper, but...
So everything is initially random small values. And then we compute the derivative of the log likelihood on the whole training set. Well, not on the whole training set, on each example, which is a next word previous context pair. And we compute the derivative of that probability with respect to all the parameters, which are the last layer parameter, the hidden layer parameters, and the word features. And we do one step in the direction of the gradient. Yeah.
I guess I've got a question also about the C's, because the features are a linear transformation of the vector that contains a 1 that indicates the word.
Yes.
And next, the first layer of the neural network is also a linear transformation.
So together
So they could be.
No. Well, I see what you're.
There's no nonlinearity between.
Yeah, but you don't need it because the thing is here you're exploiting is the same C here is reused for all the words. So if I was not doing that, so if the whole thing here was a big matrix, then you would be right. So if I had this big vector and I was replacing this by a single big matrix, then what you're saying would be true, and it would be useless to have these two layers. But because I'm structuring that linear transformation with these submatrices which are shared, what I'm doing is I'm trying to say, well, the representation of a word doesn't depend on whether it's the previous one and the one before or something like that. And I'm going to take advantage of that.
Basically, the product of the matrix has low rank, the two matrices has low rank,
Yes,
and you're
yes,
enforcing that.
yes. So I have less free parameters than I would have otherwise.
There's still a linear transform.
It is still a linear transform. The whole thing here is a linear transform, but with constraints. Yeah, exactly. Okay. So I have a tech report on the web that you can look at to see some of the experiments in more detail and some of the things we learned by doing these experiments. So the last 3 columns are perplexities on some pieces of Brown, and we tried things like seeing whether the hidden units are useful or not, and they are. Trying to see if the direct connection from this direct connections possibly between the this level. So now we have another vector here, and then we have this, and then we have this. Okay. So we can have also direct connections from here to here. Initially I thought they were useful, but they don't seem to be in these experiments. A lot of little things you can play around with the architecture and see how it changes. If you select whatever architecture that works best on the validation set, and then, one trick which helps a lot, of course, is that you can take the resulting network, which here I say has a perplexity of 276, and you just add it to the n-gram. Just do half of the network plus half of the n-gram, and you get a much lower perplexity. Because essentially, somehow it makes errors in very different places.
So what are the left? MLP1 is
Yeah, it's just different architectures that I tried. And this says like
nothing to do with how long the memory is.
Yeah, so this is the memory. This is the number of words of context used.
Yes, okay.
So for example, here we see that going from 2 to 4 is helpful.
When it's 2, that's a trigram.
Yes, this is the trigram, the last thing. So adding context helps. And of course, with Brown, at some point, if I put more context and more free parameters, it can overfit. But on larger data sets, I've not been able to overfit. And the main challenge here is to get this to run faster, because on Brown, I can train this in a day or something, or on large data set, it takes weeks, which large meaning just 15 million words. And so that's not acceptable. These are some results I obtained on some pieces of AP News with 14 million training words. Again, we can do as well or better as the trigram, but it's painful to get those results.
What happened if you had an n-gram or n was more than 3?
N more than 2? Yeah. Well, this is trigram, right?
Yeah. So what was it to a quadgram or something?
Oh, I didn't try. You might get better results. It's quite possible, and you can surely probably, well, according to the literature, you should be able to do better with some sophisticated back-off models. I use deleted interpolation.
Right.
So I'm not saying this is the ultimate thing, but it's encouraging that you can use this.
But presumably it's a lot easier just to HTTP down like vast amounts of text, and then just train a trigram model, which is very quick, rather than using your much more complex
Sure.
approach.
Oh, I agree. I totally agree. But at some point, if you want to capture higher order dependencies with more context or more structure in what you want to put in, then the n-gram model is going to be limited because of the reasons I explained before in terms of the curse of dimensionality and so on. And so I think it's worthwhile to explore these other methods which can, in principle, represent very high order dependencies with a number of degrees of freedom which is just what you need according to the amount of data you have. So I don't think it's something that you want to use right now in your speech recognition system. I mean, the improvement is not big enough compared to what you have to pay for it in terms of training time. Yeah.
So to follow up on Miles's question and your answer to it, do you have a sense of how you might use this method to deal with larger windows?
Oh, well, it's trivial to use a large window here.
Well, I'm talking about the whole sentence, for example.
Well, at some point I did some experiments with 8 words of context. It works fine. So, because the number of parameters doesn't grow, the only problem is that with a small data set, with like Brown, 8 words of context is not buying you much because there's not enough data to take advantage of it.
Well,
and then for a large data set, it just takes too much time to train. And that's why I'm working on ways to make it faster. Orders of
my
magnitude
question is,
faster.
for example, do you want to tie parameters across
What?
history? Do you want to tie parameters across histories earlier than a trigram, for example? In other words, at some point it just becomes generalized context, right? So when you're dealing with very large histories, you have the issue that sentences are different lengths to start with, but
Yeah.
But there's also the issue of whether you want to represent any
I don't think that's a good
relationship between words, which is more interesting than
I agree.
they occur at a distance of 13 from each other.
Yes, I agree. And there are ways to try to put that kind of information in neural nets. For example, one is so-called recurrent neural networks, where you build a representation of which summarizes the past recursively. So it doesn't depend on the exact position of the previous word. And something in between the feed-forward net and the recurrent net is called a time delay neural network or convolutional neural network, but I'm not going to explain that. So there are ways to try to avoid the fact that with this kind of representation, just like the n-gram, I'm using different parameters depending on whether it's the 8th word or the 9th word, which is kind of strange. I agree. All right, so let me skip that.
Skip that. Can you just skip that?
Well, it's 11:30, you know. Let me frighten you a little bit here. So I guess
let's have a moratorium on questions for the next 15 minutes.
Okay.
So we get to more than the third line, which is probably where we are now.
Okay, so this kind of model that I talked about is, so this is a Maxent model. And in general, it's part of a larger family of models which are just computing some function of the variables of our interest and then doing some normalization, which Hinton calls energy-based models. And now these kinds of models are interesting to contrast with mixture types of models. So things like HMMs, for example, are mixture models. And this is very different from these neural nets or max entropy model, which are not adding probability, but multiplying probability. You can think of each of the hidden units or each of the feature in a Maxent model as a little model that only sees part of the world and then predicts something about the thing you want to predict, the probability. And then you're taking all of these little experts and multiplying them their probabilities. All right? Because what you're doing is you're adding in the log domain. And so this is essentially really multiplying those probabilities. And there are experiments, for example, by Foster, some of my colleagues in Montreal, where they compare, for language translation, adding versus multiplying. So in translation, to predict the next target word given the source sentence and the previous target words, what you could do is have, because this just has, like, again, our table is not big enough, we can't capture all dependencies together. We're going to separate the two kinds of dependencies, and we have a model which tells us the probability of the next target word given the source sentence, and another one which tells us the next target word given the previous target words. And then we can either make a mixture of these guys or we can just multiply them.
I'm not, previous target words is the same thing as source sentence.
No. We're trying to translate from source sentence to target sentence.
What is a source sentence?
We're
That's the brief.
No. We're
No,
translating. Translation.
Oh, I'm sorry.
Okay, so
Yes.
source is in French,
Yeah,
target is in
I'm
English.
sorry, I was still in speech recognition. Right.
Right? So, but basically the point is we want to predict this thing, and there are two types of variables, these guys or this guy, and we can make two models. One just uses this information, one uses just this information. And then you can either take a mixture or you can multiply them and then normalize. And of course the product version is more expensive because you have to deal with the partition function and so on, and this is the Maxent approach. But interestingly, it gets a really drastic improvement in perplexity in this case. And there are experiments on stochastic grammars where by Charniak also suggesting comparing kind of maxent combination versus deleted interpolation combinations that show interesting improvements. So to summarize, why am I talking about that? Because there's maybe a bigger message behind this, which is that when you combine little probability experts together by addition, by a mixture, you can only dilute probability mass. In other words, the probability function cannot get more peaky when you do a mixture of different contribution. It can only get flatter. Whereas when you multiply, you can get more peaky, right? So somehow there's a kind of power that you get with products that you can never get with just mixtures.
Doesn't that give you more room to ham yourself by?
Sorry?
Doesn't that just give you more room to ham yourself by, i.e. you're going to overfit?
That's another
You're
issue.
adding if you don't.
That's another issue.
Level multiplication if you trust it.
All right, so speeding up, let me tell you quickly, because I'm not going to have so much time, on a thread of research that I've started to try to speed up these neural nets. Or actually any other model where you have your probability represented by normalized functions which depend on your random variables with some parameters. So the idea is that the gradient, which is what you need for learning, you can write in this form. So if you just do a 2-line of arithmetic, you can see that the gradient, which is in which direction you should change the parameters of the neural net, for example, has one contribution which tells you you want to increase the probability of the observed data. This is what this is saying. So you have a kind of force that pushes up the probability of the observed data. And at the same time, you want to push down the probability of all the other possible occurrences, which in the case of conditional probability is all the other possible next word, for example. Now, this pushing down is weighted, so we have really an average of those gradients for all the words weighted by their probability according to the same model. And if you look at the computation that is performed in the neural net, the really expensive part is doing that sum. If we could just get rid of that sum and just keep this thing, it would be much cheaper. Because if you have 20,000 words in your vocabulary, somehow you have to do 20,000 computation here to get this part of the gradient. So the idea of the sampling methods, which are inspired by the contrastive divergence idea of Jeff Hinton, is that we're going to approximate that average that I had in the right-hand side here. We're going to approximate that sum by a sample. In other words, we're going to choose a few words, few J's, not all of them, maybe 100 of them, and we are only going to compute the gradient for those J's. And this is just like Monte Carlo approximation, right? This is an expectation, and we're going to approximate the expectation by an average. And what we're going to get with that is a noisy approximation of that sum. But it doesn't really matter because this is noisy in the first place, because this is not the complete gradient. This is only a gradient for one example. And we're doing stochastic gradient descent, which means we only take the gradient for one example or a few examples, and that tells us, and then we change the parameters.
The PJ that's in that sum is really
the neural net
shorthand notation for
the
right hand side.
Yes, for that.
Yes.
Yes.
Right.
Yes, exactly.
It's not the true PJ. It's
No. It's the model PJ.
Yeah.
It's not, there's no true PJ.
When you sample words here, you're not sampling uniformly, right? You're using important sampling or something.
Yes, I'm using important sampling. Right. Yeah, well, so if you were to do straight Monte Carlo, you would have to sample from P, but you don't want to do that because it's going to be too expensive. To compute P costs you a lot because you still have to do this numerator. So instead of sampling from P, we can sample from something else. And we can use a proposal distribution. and we're going to use something like importance sampling, which is a sampling method which approximates Monte Carlo by sampling from another distribution that is easy to sample, for example, the unigram or the n-gram. Now, because we're sampling, I'm going to skip that, another method. Because we're sampling from the wrong distribution, we have to make a kind of correction, which is what the importance sampling is about. And the correction you have to do for importance sampling is just to weigh the samples by the ratio of probabilities of the correct to the correct probability to the proposal distribution. So if you're trying to do an integral f of x, p of x, you can approximate it by Monte Carlo by sampling from p and do an average of the xi. Okay, this is Monte Carlo. Now another approximation. So we sample n things from p, but we don't know how to sample from p. So let's sample from q. Okay. Now, to correct for that wrong sampling, we're going to weigh these things by p over q. Okay. Now, we're still not out of the woods because we don't really know p, which we still need here for the weights. So we use another approximation where, which is the one here. Okay. So the thing we want to average is the gradient, and the ratio of probabilities is this one, except this one misses the normalization constant, the z, the partition function, right? Because p is e to the output of the neural net normalized. So this is p over q, but without the normalization function. So, and this thing is an approximation of the normalization function, which we obtain by importance sampling also. And this is a kind of standard approximation to importance sampling when you don't know the partition function. And using this kind of thing, we are able to get a speed up of about 25 on our Brown experiment, which is already quite interesting. Now there's some little hacks and still things that we have to work out, but I'm going to skip that now. But I think we can do much better. I mean, the potential speed up is like 20,000, and we got a speed up of 25.
Why do you say that? Why is it in the million?
No.
Why is it 20,000?
Because we're replacing a sum of 20,000 elements by replacing that sum by a sample, and the smallest sample is 1. Okay? So that's the speed up of 20,000. But you're laughing, but I think it's possible to actually get there.
Well, maybe 10,000.
Yeah. All right. So one thing we're working on is to improve on that is to adapt. So instead of using a fixed proposal distribution like the unigram or an n-gram, we can adapt, we can learn a good proposal distribution. So we can use something like a bigram representation, which is easy to sample from, and essentially learn a bigram which has the property that if we use that proposal distribution, we have the smallest variance estimator. So we have the best estimator in some sense that has less noise, and we can figure out what's the ideal importance sampler, which of course we can't get, but we can approximate it with the constraint that it has to fit in a table of next word given previous word.
How much is the difference between the full solution and the approximate solution?
Well, so the full solution is going to cost us, say, 20,000 times 10,000 multiply add for each time we want to compute the probability of a
solution. Like, is it like?
Oh, with the approximation we get the same perplexity. We get down to the same perplexity. So in, for example, with 8 epochs, which is all we need really for Brown here, we get the same perplexity as if we use the true gradient. So the idea is working. There are some details to get it to work better, and I'm going to skip things. And now let me apparently change subject. One thing that's missing in this neural network is, as I said, the representation for a word. Really, there should be a different representation for different meanings, different senses of the word. And so I'm exploring sort of baby versions of that idea. How can we use things like WordNet to capture statistics of disambiguation, of the relation between senses of a word and the word, and instead of having bigrams that tell me what's the probability of the next word given the previous word, suppose I had a bigram that tell me the probability of the next sense given the previous sense. All right? But of course, I don't know what's the previous sense and the next sense, so these are hidden variables in the graphical model. The only things I observe are the previous word H and the next word W. So this is one thing we're trying, but there is a more sophisticated version to take more advantage of WordNet. Well, okay, first of all, you have to realize that now the parameters of the model are P of Z given H, so the probability of the sense given the word, and this is a very sparse matrix because WordNet tells me for this word there can be only like 3 possible senses. So it's an extremely small matrix. Then there's this matrix which is also very small in the other direction for the next word. Now this one is big. It's actually bigger than if I had a direct matrix here, because for each word here there may be like 5 senses and here 5 senses, and so this is like 25 times bigger than a bigram matrix. All right, but we can deal with it. The next thing we can do to use something like WordNet to smooth the bigram even more is to introduce another level of hidden variable, which tell me, for example, that when I see cat run, and then there are the 2 senses which are the usual senses for cat run, it could have been dog walks, okay, because cat and dog have a common ancestor in the WordNet ontology, and walk and run have a common ancestor in the WordNet ontology. So I'm going to introduce 2 more hidden variables which correspond to high-level ontological categories. Now, this matrix, which tells me which high-level category correspond to which sense, is also very sparse. I'm going to learn all the parameters of all of these arrows, all of these matrices. This is going to be sparse, this is going to be sparse, this is going to be sparse. The only thing that's not sparse is the bigram. Now the bigram tells me what's the probability of having some high-level concept followed by some other high-level concept. All right. It doesn't have more entries potentially it doesn't have more entries than the regular bigram because they're about the same number of concepts as words. But it's much less sparse because now each time I see a pair of words here, I'm going to give some probability to all the neighbors for this guy in the ontological space and all the neighbors of this guy in ontological space, and then I'm going to say, well, they could have been paired. So it's going to take, but it still fits in memory for bigrams. It's not going to fit in memory for trigrams, unfortunately. Anyway, with 2002 computers. But in any case, eventually, I want to have this thing not being a table, but a neural net. The reason I'm doing that, I want to study how we can use prior knowledge about senses and ontology to smooth those probability tables in a simple way that is easy to understand. Actually, the thing that I showed before is not going to work for a subtle reason, because what this mapping from here to here is doing is smoothing, all right? Because it's saying I'm going to discard information about the particular sense that I have here. I'm just going to use some higher level concept to predict the next whatever. So this is throwing away some information. The higher up I'm going to go in the hierarchy, and the more I'm going to be smoothing. So the probabilities in that matrix are really smoothing probabilities. They tell me how much probability mass and how far away I'm going to give away when I see a word to all of its semantic neighbors, where semantic neighbors is defined in some sense by WordNet. So this arrow is a smoothing parameter. And unfortunately, this one is also a smoothing parameter because I'm choosing the level of the next word. If I choose a very high level, then I can predict a lot of things here, so it's a very diluted probability. If I choose a low level, I'm going to have a higher probability for the word here. So this is also a smoothing parameter. So ideally, I would like to learn the smoothing parameter on a validation set. Like in deleted interpolation, you learn the smoothing parameters on a separate set. But this is a huge matrix. Most of the parameters are here, so it can't be both in the training set and in the validation set. So that's why I have a variation here that finesses that problem. Now I'm going to not talk about that.
You should probably wind up in the next 5 minutes.
Yeah, so I'm going to instead talk about getting back to the neural net. And now using this ontology and polysemy business, suppose the input of the neural net now was not the words, but the sense of the word. Suppose you knew what the correct sense of the words were. Then you could put in input of the neural net the information about which sense was observed, and the neural net would predict the sense of the next word given the senses of the previous words. And now that's one step. And the second step is saying, well, I'm going to take advantage of the ontology by saying, in input, I'm not going to have just a vector with a 1 at the place corresponding to that sense. I'm going to have also some 1s corresponding to higher level categories in the ontology that are consistent with that sense. So if I have cat here, I'm also going to turn up the bit for pet and the bit for animal and the bit for animate object or whatever. This is going to give me automatically some kind of generalization to these ontological neighbors in the context of the neural net. Now, so that's one thing, but of course I don't observe those senses. So what I can do essentially is, assuming the running of the neural net was not as expensive as it is now, I could search, just as it's done in, for example, lexicalized stochastic grammars, I could search for the sequences of senses that are likely jointly with the sequences of words, and run these sequences of senses through the neural net. And then using the posteriors and blah, 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 we can train these things properly, in theory, of course. Now, it's going to be much more expensive than the first neural net I had, because now instead of running the neural net once when I have, say, a sequence of word, I will have to run it, say, 100 times, because well, maybe not 100 times, maybe say 20 times, because maybe there are 20 different sense sequences which are likely to correspond to that sequence of words. All right? So, well, similarly, you can plug in these things in, you can put in grammar outside, so outside of the neural net. Or another way to put it is you can put the neural net inside a lexicalized grammar. So the idea is, in the lexicalized grammar, you have tables of probability, which tell you things like what's the probability of the next word, give you a bunch of information about previous heads and tags and stuff. Now, instead of having these tables where you have to make hard choices about what you can put in context, you can have a neural net or something like that, which possibly has more things in input. And you can train these things in the same way that I only said a few words before about using the posteriors, which is essentially similar to what you do when you use Maxent. Okay? When you use Maxent to train these guys in the lexicalized stochastic grammar. Except it's more expensive than Maxent, but the principle is exactly the same. You use the same information, use those posteriors to tell you how you should move the gradients, how you should move the parameters of the neural net. And now, since you're going to use search anyway, instead of using words as input to the neural net, you can use senses, and you can use this trick of putting in their ontological ancestors. So you get this free generalization to neighbors that is learned by the parameters of the neural net. So, of course, all of these are very speculative, because I have not implemented any of these things, the recent things I've talked about. Although a few are almost done. This is obviously not done, and it's not going to be done until I can get the neural net to run much faster, which is my first goal. So that's it. Yeah. Well, there was one bit of thing, kind of speculation in the speculation area, which is that I think that if we want to go further in natural language, statistical language modeling, we have to go beyond texts. And the argument is that if you only observe text and you want to capture semantics of the text, you have to somehow associate the text with other things. Otherwise, maybe you'll be able to do it with tons of text, but it's going to be much less efficient. In other words, if you only hear someone talking and you don't know that language, eventually you might be able to capture something about those dependencies. But if you also see him move, you probably can learn much faster what's going on. All right? And the one extreme case is you can imagine a language where, like a primitive language, which is not compositional, for example, where, say you have some animals talking to each other and they have a vocabulary of 10,000 words, but each word is a complete semantic unit. And then, like danger, there's a big cat coming. But that's one word. And then if you just see all those utterances, they don't tell you anything. The only thing you can capture from the statistics is like the frequency of occurrence, the unigrams. And there's nothing else to capture. If you really want to know what they mean, you have to see those utterances in the context of other things. And we actually have now a lot of sources of information, like bilingual texts, image database, videos, web pages, that allow us to associate text with other things. So that's kind of an unrelated thread for much longer term research.
About 1 minute of questions.
I have a question about these internal representations for these words.
Yes.
So you really want to get at a more compact representation of your word, right?
Yes.
So,
well, at least for computational reasons.
yeah. So if that was the case, shouldn't it be also the case that if you were to train, say, an N-gram model, instead of your actual words, if you replace the words by the internal representation,
Yes.
shouldn't then the complexity go down? So if you...
I'm not sure I understand.
So,
well, you can't do that. Well, those features are continuous.
So if you take a B and C, and then, and you have your trained network, right? So that trained network is going to give you an internal representation for each of these words.
Yeah.
So then you create a copy of the B and C where you replace all your words by the internal representation.
But the internal representations are continuous valued. I can't use them as index in table.
Okay, yeah, but
this is what the neural net is trying to do with the upper layer. What you're doing, what you're saying. Yeah.
Word disintegration in a general context is it's usually a hard problem. Word sense disintegration is a
Yes.
hard problem.
Yes.
It's performance around 65%.
Uh-huh.
This would very much hinder your performance of the neural network.
Yeah, so the ambiguity is something that's probably hurting my current neural net. That's why I'm exploring, and this is just an intuition I have, I don't have any proof of that until I tried the kind of experiments I talked about, where I put an input of the neural net that disambiguated senses. And I put an outer search loop, which essentially tries all the likely sequences of senses. Okay, and then I will be able to say whether that bought me a lot or not, because now it's trying to learn representations which kind of merge all the senses of each word, and if they are very different, then it's probably not nice. Yeah.
Comment. So it might be worth your time spending a little bit of time trying the most state-of-the-art smoothing method. There's standard language model toolkits. For example, Andreas Stolke has a toolkit, the SRI language model toolkit, which is freely available and it's quite good. And it would take only a few minutes. It's actually quite fast. It would take a few minutes to train the corpus and compute your perplexity numbers on exactly the same corpus you're doing using, say, Kneser and Nair. Many of the sort of the standard ones which have repeatedly shown to significantly reduce perplexity.
Yeah, actually, I didn't do that, but I had some a lot of discussions with Josh Goodman, which kind of put all these things together. And he took the same data that I used for Brown, and he put all these tricks and the same data, and he get about the same perplexity that I got. So essentially, I'm not able to.
That you got with your neural net?
Yes, yes. So I'm not able to beat the best state of the art. I'm doing about the same as the state of the art on Brown. But, you know, I think.
I guess I wouldn't even call it all these tricks. It's quite straightforward.
Yeah, I don't know enough about these things. For me, it's more complicated than these neural nets.
But still, if you combine and
Yeah.
performance, and
Yeah.
increase in performance.
So the kind of 20%, 30% improvement I got, you can get with you know, the best smoothing tricks.
You can still do that with the best smoothing techniques to necessarily, and then interpolate it with the
Yeah. So yeah, it could be. I could get better results by mixing the best smoothed n-gram with my neural net. But that's not really my. What?
Or multiplying them.
Yeah, or multiplying them. Actually, that's right. I should multiply them. You're right. And I should probably do that. But I guess I'm aiming for farther away when I can get this to work on large corpora where there is more information, more high order dependency to capture.